Hello everyone and welcome back to the fifth tutorial of this video series in which we are looking at how to use the MatPlotLib library to teach mathematics and physics, especially to use visualization tools to better present your lessons. So for the first section we're going to be looking at multivariable functions. And the first types of graphs that we're going to be looking at is the contour plots. So basically this is like looking at a geography textbook and looking at a mountain from above, which then displays like the contour lines where the height is specified based on that contour line. But let me just reset the kernel and then import the appropriate libraries. In this case, we're going to be relying on the MatPlotLib library and the NumPy library. And one thing that we need to do is, before we plot anything, we're going to require this concept of a mesh grid. So for that, I'm going to introduce the dimensions of our graph, because we're going to have two-dimensional plots. Okay, so it's going to have an x-axis and a y-axis basically, and then a z-axis coming out the page. But we really won't see the z-axis, it's just going to be the contours. Okay, so that's how contour plots really look. But for this, I need to call the mesh grid method mesh grid, and inside I have to pass in the dimensions that we've just specified using the linspace method. Okay, so the mesh grid basically comes down to two-dimensional linspace. So let's look at what this x and y looks like. And so that's a 2x2 array values. It's taking all the x and y values that we've specified in the linear space. Okay, and then we're going to define a multivariable function z, all right, and that's going to be x squared plus x times y. And then we're going to use the plot.contour method, and we pass in those mesh grid x comma y together with the function, and then we want to specify the number of levels that we want to see in our contour plot. So that's just going to be the number of lines basically. Okay, so it gives us this beautiful graph. That's the levels. It's 30 contours will be visible to us. We can actually increase that. Let's increase that to 100 to see what the effect may be. Okay, and if you look at it very closely, you can see that it's much more dense. Okay, we can go all the way to as many as you want. Okay, just as an alternative example, here I have the function z, which is x squared plus xy plus y squared, and it's something similar, although it's more elliptic. Okay, so it's sort of like concentric ellipses around us, around a point, and we can reduce this levels number to 30 just to see that it looks a bit more readable. But the advantage here is we can also adjust a lot of the other parameters, right? And one of the parameters that is really important is that we might want to add C labels to our contour plot. So firstly, you have to give your contour plot a name. I'm going to call it CNT for contour, and then I'm going to also instantiate a new method C labels, and inside of that I'm going to pass the contour plot variable that we've just created, cont. Basically what it's going to do is it's going to add values to our contour plot to specify the height of each contour, so to give it that three-dimensional effect, readability. So you can now use this in your geography class or anything like that. Alright, so here's another example, same concept, really nothing's changed. I'm just changing the function z, which is x squared over 7 plus y squared over 5 minus 1. Okay, and that's basically the equation of an ellipse. So once again, concentric ellipses about a point with different depths. And so that's really cool, because I'm sure you haven't seen much of this before. We can also add another feature to this graph, which we call the color bar. So to do that, really all you have to do is to call the color bar method on top of your plot. So because we've already instantiated the plot over here, all you got to do is, let's say, plot.colorbar, and then it's going to give us this sidebar here, which then tells us that the heights of these contour lines are associated with these color keys. So the very dark purple one, the most inner circle or ellipse, is associated to -1, and the green outer contour, which is almost nearly not visible in our grid, is at -0.64. Okay, so that's really cool. If we can actually combine both of them at the same time to have both C labels and color bars. So it's going to look like this. Now we have our C labels right at our contours for readability, and we have our color bar on the side of our graph. A different type of contour plot that we can have is what is called a contour filled graph. Okay, and all we have to do now is to specify contour f instead of contour. So I'm going to use the same example over here. Z equals x squared plus xy, right? And then instead of just saying contour x, y, z levels, just going to say contour f. And that's going to give me a filled grid. It's giving you an effect of depth, right? So that's really cool. I can also add a color bar to the contour f method, right? So instead of just having contour and then a color bar, it can have contour f together with color bar. And I can give my color bar a label, which in this case I'm going to call it color bar. Alright, and it's going to look like that. Once again, I can adjust some of these parameters. If I want more levels, for example 100, it's just going to be a more blurred effect on the graph. If I want to see more of my lines, then I'm just going to keep it at a shallow level, like 30 or something. Vmax and Vmin is basically just going to specify how much the colors should range from one another. So let's say 0.5, for example, then the contrast is quite high. These are parameters that I think you can play with. Within the contour F method, we can still add a C label as long as you give your contour F variable name, like contour, in my case CNT. And then within that C label method, I'm just going to pass that variable CNT. I can change the font size, and I can also change the colors. The reason I'm changing the colors is so that the colors of our whites are visible on top of our filled contour plot. So you see the effect of that. So if this were black, it would almost be invisible on my graph. So I've chosen to make the colors to be white. Alright, that's cool because I have a filled contour plot, and I also have my C labels over here. I can also obviously then add the color bar to that, so I can have all three at the same time: a filled contour plot with C labels and a color bar. And it's going to look something like this. Looks really cool. So this is really useful for any type of subject, really, for multivariable calculus, all the way geography, and anything in between. Alright, I can change the colors. An easy way to do that is just to specify the C map, color map, inside of contour F method. Okay, all you have to do is we just have to take the attribute CMap and set it to a valid color scheme. In this case, I'm just going to choose plasma. There are others. I'm not sure what all of them are. You can just check online and find some examples. So here's the nice thing, is that we can also still do all of this within a set of axes. So in this example here, I have a subplot, axis 0, 0, axis 0, 1, axis 1, 0, and axis 1, 1. And in each of them, I'm doing something a bit different. In the first set of axes, I have a filled contour with levels 10. In the second axis, I have a filled contour with levels 10 as well, but with a different color scheme. In the third set of axes, I actually have the same thing as in the first, except that it's not a filled plot, it's just a normal contour plot. And in the last one, I have a contour plot with a different color scheme as well. And so I'm going to get this series of plots, like 4 different plots all together. And for each of them, I can adjust their parameters independently. So for example, if in one of them I want to have the color bar, I can. If in the other one I would like to have a C label, I can also do that. So that's what I have over here. So for the first one, we just have a normal filled contour. For the second one, we have a filled contour with a plasma scheme color. In the third graph, we have a contour plot with contour labels, right? So there's numbers associated there for each contour line. And in the last one, we have a contour plot, right, with nothing but a color bar, okay? So that just means I have to set the axis 1, 1 as the axis which takes the color bar with variable name contour. And so I'm going to get that, all right? So that's cool. We're now ready to talk about the next section, gradient or vector fields. Inside of MatPlotLib, it's called quiver plots or phase plots. So this is really useful when it comes to differential equations. Often in differential equations, you need to visualize the direction of a field, right? So this section is gradient or vector fields. Inside of braces, I'm just going to put quiver or phase plots. Okay, what that comes down to, as I said, is fields. Alright, so let me just reset the kernel. Alright, and let's import the appropriate MatPlotLib library and the NumPy library. Almost everything is the same as within contour plots. The only difference here is that instead of calling contour plots, we're going to call quiver plots, because I'm still going to make reliance on the mesh grid, which takes as argument 2 linear spaces. In this case, I've only defined 1 dimension, but I use it in both my arguments for the mesh grid method. And then I also define these 2 functions based on x and y. These are multivariable functions, u and v, that is defined as -1 minus x squared plus y, and v is defined as 1 plus x minus y squared. Okay, and then I instantiate a plot. And on my axis, I call the method quiver, and I pass in both x and y, those are my dimensions. And then I also pass in the 2 functions, u and v, and I also just set the aspect ratio to equal so that it's not really distorted or anything like that. and I'm going to get this grid of arrows that point in the direction, in some sense, that represents a field. Alright, so depending on what subject you're interested in, this is really useful for differential equations. Gradient fields, derivative are represented in terms of direction often, and the length of the arrow normally represents like the magnitude. So that's pretty interesting and useful when dealing with like concepts or anything really in physics. Here's another example where we have declared a mesh grid based on the dimension a range starting at 0 going all the way to 2.2 in incremental values of 0.2. Then I have my two functions u and v, which is cos x times y and sin y times x. I instantiate a subplot and I call the quiver method. I pass in my mesh grid values x and y, pass in my functions u and v, and I set the aspect ratio to equal, and then I plot dot show, and then I get this vector. Alright, so that's pretty cool. Here's a more interesting one, which has sort of like vortices. Right, so I have my a range dimension, which is 0 all the way to 2 pi plus 2 pi over 20 in increments of the 2 pi over 20. And so now I have my mesh grid, which is based on that dimensions. So it's a two-dimensional array. And then I have my two functions, sine x times cos y and minus cos y times sine x. I instantiate a plot, I call the quiver method, and I pass in my mesh grid values x and y, I pass in my functions u and v, I set the aspect ratio to equal, and I show my function. It gives me this vortices. So I'm not really going to go into the mathematics of all this. This is really stuff that I think the more advanced user will be doing. Alright, these are just examples of how you can use the quiver plot to draw graphs if in case you need to be able to do like vector fields. And this is mostly useful, as I said, in physics and stuff like that. Here's an example where we have a grid of a 4x4 set of axes. We instantiate the dimension starting at -2 all the way to 2 in increment values of 0.2, and then we have our mesh grid, which takes those dimensions and makes a two-dimensional array. We have our two functions u and v, that's y times x squared and x times y squared. We instantiate a plot. Then we have four axes inside of the same figure. The first axis is a quiver plot. The second axis is also a quiver plot, as well as the third and the fourth. So in this case, I didn't actually distinguish amongst any of these. They have the exact same plot amongst each of them. Okay, it's just to get us started. But if I wanted, I could have had each axis have a different plot. So in this example, I have the first set of axes, which is a quiver plot. The set aspect ratio is set to equal, and the title is function. Alright, for the second axis, I have a quiver plot. The axis is equal, and the title is gradient. On the first set of axes, I'm just going to plot u and v, and on the second set of axes, I'm going to plot the derivative of this function z, okay, which I'm going to call dx dy, basically dx comma dy. Alright, so basically that's the derivative of the function z, which is a function of x and y in this case. Okay, that's going to give me two graphs over here. That's a 2x2 set of axes, and I'm going to get function and its derivative. So that's what these gradient vector fields are really useful for. Okay, so here's another example. Instead of using quiver plots, we can also have what is called stream plots, and that's very similar to this. The only difference is that we're not really calling on quiver plots, we're calling on stream plots. So the example that I have here is we have a linear space, okay, which I call dimension, and then I create my mesh grid, which is a 2x2 array, and I have my two functions u and v, and then I define this variable called speed, which is the square root of u squared and v squared. Alright, so that's just going to define the magnitude of the arrows, basically. And then I also have this piece of code. The first line is the line width, which I want to be dependent on the speed we've just defined. That's the speed times by 5 divided by the maximum value of all the values amongst the speed. Then I instantiate my figure as a subplot, and I have four sub-axes. The first axis, I will be drawing a stream plot. So that's the new thing that we're looking at, is what's called a stream plot. And I'm going to plot the mesh grid together with the two functions u and v. In the second axis, I'm going to again draw a stream plot, but I'm just going to change the color, and the color is going to be varied depending on the speed. And the third axis, I'm going to draw a stream plot again, but the line width will be adjusted according to our value for the variable LW, line width. And then the fourth set of axes, I will adjust the line width as well as this the color depending on the speed and the line width. And so when I render that, I'm just going to get this beautiful 4x4 grid of axes of graphs. So as you can see, if you zoom in on this, The first graph is basically just lines with having the same uniform width throughout, but the last two graphs that I have here, they kind of dim out as I get closer to the edge of the line, and the very final graph is like really the most beautiful because its color also kind of fades and it changes from like green to purple. So yeah, that's what I would like to conclude in this section. So in this section, we're going to be looking at 3D plots. So let me just reset the kernel and then import the appropriate libraries. So we're going to be using the MatPlotLib library, and we're going to be using the NumPy library. And so the first example is basically just a skeleton for the three-dimensional axis in which I instantiate a figure. I call the axis method, and then I set the projection attribute equals to 3D. And when I plot.show that, it's just going to give me a three-dimensional set of axes. And I've not yet at this point drawn any graph on top of that. And so the first thing we're going to do is just to provide it with a scatter plot on the axis. So I'm going to call the .scatter method and then pass in 3 numbers, which are the coordinates of my point that I would like to render on this axis. So it's going to be on 5 units on the x-axis and 10 units on the y-axis and 8 units on the z-axis. And so it's going to give me this. For another example similar to this, we can just use the plot method instead of the scatter method, and then also pass in 3 points in a list form. So I have here x1, x2 and x3, and then I'm going to pass them in as points in my plot method, and I'm also going to specify that I want the marker style to be little o. Upon rendering that, I get 3 points. Since this is the plot method, I can also pass in a line style attribute, in which case I'm just going to call it the dotted line. And so now all 3 dots are connected in that order, x1, x2 and x3. So what's nice about this scatter method is that I can also generate a list of values. For example, here I have x data, y data and z data, which are all random integer values between 0 and 100 of 500 values each. And the marker style of each is the greater than symbol, which is just going to render as little triangles. And so I'm going to get this graph over here, a really nice 3-dimensional scatter plot. Okay, cool. I'm going to use the same example and just adapt that a little bit. We're going to define the variable z data as the relationship between x and y, the product of x and y data values. Okay, but in this case, I've just replaced the linear space method with the arrange method. So that's going to give me values from 0 to 50, all separated by 0.1 units apart. And so in the plot method, I'm just going to pass in the x data, the y data, and then the new function z data. And so it's going to give me this curve over here. So I can draw many different types of objects in a 3-dimensional set of axes. So we've looked at plot, we've looked at scatter, and we've looked at the different types of variables that you can pass in. Here's another similar example to this one. The only difference really is that my linear space is the z-axis, but my x and y values are defined as sine 25z and y is equals to cos 25z, all times by the value z. All right. So if I run that, I'm going to get this vortex spiral shape. That's really a cool shape. All right. So yeah, here's another example that kind of simulates the idea of curve fitting. So I'm going to have a line plot and I'm also going to have a scatter plot. So for the line, I'm going to declare the linear space 0 to 15 of 1000 values. And I'm going to define the x and y line as sine of the z line and y is equals to cos of the z line. And then I'm also going to plot that just as a normal plot. And for the scatter plot, I'm just going to ensure that there is some discrepancy because I've defined them in pretty much the same way as above, but I've also added a bit of discrepancy over here. 0.1 times a random number up to 100, just so that it ensures that the values don't lie or they don't fall on the curve 100%. And so when I render that, it's going to look something like a curve fit. So in our next example, we'll have a different type of plot which relies on the plot underscore surface method. Here I've defined the variable x underscore data as a NumPy arrange from -5 all the way to 5, incremented in values of 0.1, as well as for the y values. And then we've also used the mesh grid method to create a 2-dimensional array. And so this the 2-dimensional array is then what we will use in our plot surface method together with the function z defined as sin x times cos y. And then I'm going to set the color map equals to plasma. And so this is going to really look nice. If I render that, it's going to give us this 3-dimensional surface, kind of like a 3-dimensional sine cos wave of some sorts. and it really looks cool. Another thing that we can do, we can start looking at the attributes inside of the plot surface method and so on, and change some of the axis properties and so on. So one thing that we can do is to change the view_init method of the axes. Okay, and so to do that, I have here an example where I've manipulated the azimuth angle and the elevation angle of the graph so that it appears differently when rendering the initial view. So by setting the azimuth angle equal to 50 and the elevation to 90, we get this top view of the graph. So if I play around with this a bit and make it, say, for example, 45 and minus 45 for the azimuth angle, it's going to give me that. All right. So it seems like there's nothing really different, but because the axes were rotated, then the labels are also rotated. Let's say that you wanted to say that this must be 30 degrees. It's going to give me that. All right. So yeah, you can play around with that and see what looks good for you and your purposes. Let's put a value of 10 and see what happens. Oh wait, that looks really cool. So what about the azimuth angle? If we make that something like 10 as well, then it's almost as if we get a side view of the whole graph. Later on, we can use this to animate the graph and make it rotate. But yeah, let's first look at all the other possible attributes that we can change. Another method that we can use is what is called the Sympy contour 3D method. And so here I'm going to use the same mesh grid x and y, and I'm going to use the same function, which is sin x times cos y. And then I'm going to set the color map to binary, which just means that it's going to be black and white. And it's going to give me three-dimensional contour plot. So instead of a contour plot looking from above, we now get contours that are rendered in three-dimensional space, and I can see almost all the effects of that. Another thing that I can do is, for example, I can have a wireframe. And basically, I'm just going to call plot_wireframe with the same mesh grid and the same function. And then I'm going to set the color to black. You can set the color to anything, really. Upon rendering that, I get this wireframe object. That looks really cool as well. So we have different techniques for different purposes. So you can really pick and choose what you like in your presentations. Okay, so another method that we have available to us is the plot_surface method. Is also quite useful. I can pass in the mesh grid x and y and the function z that we've defined previously. And this time I'm setting the color map to viridis. Okay, and I'm just going to remove this stuff here. Okay, and upon rendering that, I get this three-dimensional surface, which is still pretty much the same. The only difference is basically the color. But yeah, I'm also just illustrating that there are different methods of achieving the same sort of desired result. You know, contour 3D, plot_wireframe, plot_surface. Let me just give you another example of a surface that's really nice to illustrate. Okay, so here I have declared two variables x and y, which are the length spaces from 0 to 50 of 50 values each. And then I've declared this mesh grid x, y. The NumPy mesh grid takes the linear spaces and makes it a two-dimensional array. And then I have defined the function z, which is the product of x and y. Okay, and so then I'm going to call the plot_surface method and pass in all of those variables. I'm going to pass in the mesh grid and I'm going to pass in the function, and upon rendering that I get this shape over here. It's a three-dimensional surface. It looks really cool. So yeah, here's another example. All I've changed over here really is the function, which is z equals to x squared plus the product of x and y, and I've changed the color of the C map to plasma, and upon rendering that I get this three-dimensional surface. It looks really cool. Let's look at how we can use the Sympy library to draw three-dimensional graphs, because up to now we've only used the MatPlotLib library, but we can also use the Sympy library, which is called the Sympy plot 3D library. And for that, let me just reset the kernel and then also import the required libraries. In this case, I'm going to use Sympy as SMP, and from sympy.plotting, I'm going to import plot3d. Okay, and I'm also going to import the one that we always use, matplotlib.pyplot as plot. And then I'm also just going to set some of the parameters for the figure size, the axis, and this additional one that we're going to be looking at in a bit. For now, I'm just going to set that equals to 0 because I'll illustrate its effect in a bit, and I don't want to overcomplicate things now, so let's just set that to 0. So our first example, we don't really need to instantiate the figure or anything because Sympy understands that we want to actually plot a figure over here when we call the plot3d method. Okay, so I've defined my function z as x squared over 3 squared plus y squared over 5 squared, and then I've passed in this function in my plot3d method together with the domain for x and y from -5 to 5, and I've suppressed the plot so that it doesn't show two figures, and I've set the figure size to 6 by 6, and then I'm calling the plot.show method to render the graph. So okay, we've actually cleared the memory here for x. So let me redefine x over here. To fix this problem, we just declared the symbols x and y. and then we can render that graph. This is a paraboloid, and here's another example of something similar and something as beautiful. This time we're going to get this saddle shape. The only thing I've changed is that I've changed that plus to negative, and now we're going to get a hyperboloid. And you can play around with different functions. Here's a different type of function that does not look so ordinary. This one is defined as x squared times y over x to the 4 plus y squared. And the shape that it's going to produce, I'm going to plot this graph by passing in h as a function of x and y with a domain from -10 to 10 for both x and y. I'm going to suppress the plot, and so that I'm only going to render it upon showing the graph. And this gives us this sort of three-dimensional portal type of object. So let's look at the effect of the xTix major pad. Okay, and basically if I set it to something other than 0, it's just going to separate the ticks from their axes, and it's going to make them appear a distance apart from the axes. They would normally be closer to the axes. So for example, if I set this back to 0, I'm going to just get the normal axis with the ticks right adjacent to the axes. So yeah, you can play around with that and see how you feel and where you would be comfortable with placing your labels and stuff like that. Okay, so yeah, that's pretty cool. In this section, we're going to be looking at animations, and so this is really an interesting section because we can start to make our graphs come alive. First, let me just reset the kernel. I'm going to copy and paste some comments that I think you can read through a little bit because they're really important in this case. So it basically comes down to the fact that we're going to be taking advantage of the fact that we're inside of a browser, so we can use JavaScript to render our animations. Instead of rendering our pictures as PNG files, we're just going to render them using the func animation method inside of the MatPlotLib.animation library. Okay, so our first example is quite simple, and basically what I'm doing here is I'm importing these libraries that are going to be useful for animating our graph, and then I'm going to define the variable t, which is our linear space, starting all the way from 0 going up to 2pi. And then I'm going to declare this function sine of t, x equals sine of t, and I'm going to instantiate the figure and the axis as a subplot, and then on the axis I'm going to call the axis method, and I'm going to provide it with the dimensions of my grid, which is going to be all the way from 0 to 2pi, and on the range on the y-axis I'm going to specify that it should go from -1 to 1. Okay, and then I'm going to instantiate this empty plot. So our x values for our graph are empty, and our y values for our graph is also empty. And I'm going to then also define the animate function. And basically what it's going to do is it's going to take this plot and it's going to set some new data depending on our index I, and it's going to run through our variable t and update our variable t per index, as well as our values for the sine t function. And then I'm going to instantiate the matplotlib.animation.func animation method, and I'm going to pass in the figure object, which is our subplot, and I'm going to pass in the animate function, and then I'm also going to specify the number of frames that we want for our animation. And so all I'm going to do then is to suppress the func animation method so that it does not produce a plot until the point where I call this HTML animation.to_JS_HTML. Yeah, this obviously also has to be imported from IPython to display import HTML before I can render my graph, because as I said, we're using the browser to convert our picture to an animation. And so upon running that, I get this cool sine graph which has a little play button, a rewind button. So the minus makes our graph go slower, so it says decrease in speed. This takes us back to the first frame. This takes us back one frame or to the previous frame. This plays it in the backwards direction. I mean, this pauses the animation. We can also play it in the forward direction. We can skip to the next frame. We can skip all the way to the last frame, and we can also fast forward or increase the speed of our animation. Okay, we can loop through our animation once. We can loop through it indefinitely. And we can also loop in both directions, making it go backwards and forwards. So if I play this animation, it's just going to plot the sine graph from 0 all the way to 2pi. Okay, and because I've chosen this reflect, it's never going to stop. It's always going to keep doing that. Okay, so let me just show you what the increased speed does. I'm going to make it go faster a little bit. And if I click on loop, I can press play, and then it's just going to go all the way to 2pi and start at 0 again. Okay, so that's cool. I'm going to pause that. There's an alternative way of doing this. so that we require a little bit less code. For that, I'm just going to import MatPlotLib.pyplot as plot. Alternatively, we can make the JS animation the default for rendering the animations by updating the MatPlotLib.pyplot RC parameters. And I'm going to set animations.html to JS.html. So now it always knows to render our animations in the browser using JavaScript. So I'm also going to import the MatPlotLib.animation, because I'm still going to use the func animation method. And so I'm going to take the exact same example, except that we require a lot less code. In this case, all the packages or all the libraries was already imported. So I'm just going to call the animation object once I've closed my plot. And so I'm going to get the same result. So a little bit less code, but that's what's nice, because I don't have to worry about all that other HTML stuff. I'm just going to press play and show you that it does the same thing. It's going to loop through this thing again all the way to 2π and then start at 0. So that's nice, because I think a lot of lessons require animation. Well, often you would like to have a video in .mp4 video format, but the problem with this is that you're going to need to download a codec compiler, and I'm not going to be doing that because you need to install this on your operating system, and there's a little bit of tricks and hacks that you need to go through to be able to make that work, because basically you need a codec, video decoder and encoder to be able to render your animation into an mp4 format. And so here's a piece of code that will allow you to do that once you have your codec installed correctly, but I'm really just gonna like skim over that, because I think it's more than enough to be able to export your graphs as a GIF and use your GIF on any website. So yeah, we can also save our animations to our offline directory by using the pillow writer library. So from the matplotlib.animation, we're going to import the pillow writer library. So to do that, it's just this one line of code. And so now we can actually go and save our figures. So I'm going to take the exact same figure that we've looked at for the animation, and just below the any object, the animation object that I've instantiated with using the matplotlib.animation.func animation method, I'm just going to add another line here, and I'm going to specify the writer that I would like to use. There are other writers like ffmpeg, but once again, those are for .mp4 format, and I'm just okay with the GIF for now. I'm just going to save my image as GIF. So I'm going to specify any animation.save method, and inside I'm going to pass the string name for which I would like my file to be saved as. And I also have to specify the writer attribute, which writer I'm going to be using, and I've already declared that as pillow writer. And inside of the pillow writer method, I'm also just going to pass the frames per second to 25, and that should be more than enough for you to get a smooth rendering. I'm going to close the plot, and below that I'm just going to call on the animation object and render that so that I get a figure inside of my browser. And it might take a bit of a while because it's also saving the figure. And so let's go inspect that on our project directory. If I go to my directory for my tutorial, I see here I have a new file called this_is a pillow writer export demo GIF. If I open that, I'm gonna get a graph that's automated as a sine graph. It's just gonna keep looping through that. And so that's pretty cool, because now I have offline GIFs that I can use on my website. I can also use this in my video lessons and stuff like that as a physics or math teacher. So this is really useful. I can do some sort of simulations and illustrate some important content and stuff like that. Okay, so yeah, let me close that. We can still play it in the browser as well. We can also speed that up a little bit so it's not as slow. Cool, man. I mean, I'm really impressed with this animation stuff. We can also export our animation as a different file format. There's two others besides the GIF format. There's the .apng, and that's pretty much going to open up in the browser. It's still going to be an animation. If I go to my project directory tutorial 5, here I see a apng file. However, if I try and play it, it's not going to recognize the file type. If I drop it on my browser, it will open it on my browser and still be able to play it as an animation. However, I can also export this as a .webp file. And yet again, this is also going to be a browser file. It's just going to open up in the browser as an animation. So that's pretty cool. There's at least 3 different formats in which I can export my animations. Cool, so let's look at other examples. In this example over here, we have instantiated our subplot, because we're going to be drawing 2 different functions. We're going to define our frames as a linear space from 0 to 2π that is divided up into 50 points. Okay, and then we're going to have 3 empty lists. First, we're going to have the X list, which does not contain anything. That's basically going to be our domain for our functions. Then we're going to have y sign and y cos. Those are empty lists as well, but they're going to be updated based on this update function over here. Okay, over here I just have two empty plots as well. Once again, it contains no x values, it contains no y values, but it consists entirely of points. The other plot object consists entirely of a dashed line. All right. Okay, and so I'm also just going to set the x and y limits. That's pretty much the same as before. It's just done in a different syntax. And so our update function basically takes this set x and it appends the indices I to our list from this frames list over here from 0 to 2 pi, and then it also just updates this y sign list and the y cos list as if it is a function, because it calculates that using the NumPy library, and then it places that new value based on that index inside of that list. Okay, and then basically we set that data into our plot objects over here. Okay, and then I'm going to call the animation.func animation method. I'm going to pass in the figure, which we've instantiated up here as a subplot, and we're also going to pass in the update function, and we're also going to provide the frames starting from 0 to 2 pi. That's divided up into 50, and then we're going to close the plot so it doesn't render two graphs, and then we're going to call the animation object. We get this beautiful graph over here, which again we can play, and it's going to do two things simultaneously. It's going to draw the sine graph, and it's going to draw the cos graph using two different marker styles so that we can distinguish them really easily. I can also increase that. I can also save this animation offline. Let's just copy and paste that line from before, and I'm going to call this graph sine_cos.gif. And upon rendering that, I should again see this in my project directory over here. So here we get sine_cos.gif, and if I play that, it's just going to give me the picture as a GIF. Now I get my animation offline, and I can use this anywhere else that I prefer to use it, to build some teaching content or presentation, anything like that. We can still manipulate other aspects of our graphs using the previous techniques that we're familiar with, even though we're working with animations here. Here's an example. This is one of the previous examples that I've just taken and changed up a little bit. I've only just set the axis spines through the origin as I normally do, because I would like my graphs to appear to have a set of axes, and I've also set the x-ticks to none. Okay, but everything else here is the same. If I render that, it's going to look a little bit different. It won't have a box, it'll just have a set of axes, x and y, but the sine graph is still animated. I can still fast forward this graph, I can still reflect it, I can still play it backwards. I can also go back to the first frame every time, and I can decrease the speed. Everything else is the same. As I said, the only thing I've changed here is the axis spines through the origin and the rotation of the labels. As in tutorial 2, where we were dealing with the trigonometric graphs, we defined the union operator as well as the reflect operator for constructing the axis grids so that all our special angles appear on our graph. We can still go and do that. Okay, and so I'm also just going to define f and g as sine x and cos x, because I would like now to create those intervals of the multiples of pi over 6, pi over 3, pi over 4, and I want all of that to be on my animation as well. Okay, so I just have to import the Sympy library. So import Sympy add SMP. This is code that is familiar to you if you've been following along with the tutorials. I think this is coming from tutorial 3. Okay, and then I'm going to do the same for the y-axis. I've really not changed much here. The only thing I've done is that I've set the axis spines through the origin again, and this time for the x and y ticks, I've passed in the lists that we've created using the operators, the union and the reflect operators. We've created that xvals rads real. We've created the xvals rad string clean. We've also created for the y-axis the yvals real. Those are where my ticks will appear, and yvals string clean. So I get this LaTeX formatted set of axes, but now I have an animation over that, so that looks really cool. It's going to start all the way from -2 pi, it's going to animate all the way through 0, and it's going to go all the way up to 2 pi. I can also speed up that graph a little bit. I've also saved this animation using the pillow writer method, and I've passed in frames per second of 25, and I've also saved it under the name of example4.gif. So when I go and look in your project directory over here, you'll see it says example 3 and 4. So let me click on example 4, open that, and see this beautiful GIF image. Now you have all the tools to be able to be the best educator or lecturer or teacher that you've ever been. And so now you can present yourself as a specialist in the field of teaching maths, etc. So yeah, cool. And I'm going to give you another example in just a bit. So now we have really cool tools to be playing around with animations. We have almost everything available to us. So in this section we're going to be looking at the traveling waves, and everything else is pretty much the same. The only difference is the way that we define our animate function. Okay, so here I have instantiated the plot, and I've set my x and y limits on my axes so that our graph starts at 0 and it goes all the way to 2. Alright, so you can make that to 2 pi or whatever you feel. And on the y-axis I'm going all the way from -2 to 2. And then we have the same thing as before. We have we've instantiated the plot with no x values or any y values, and then we've specified that line width should be 2. And I've defined two functions. I've defined the init function, which is just going to set no data into our plot, and it's going to return that line variable, which is our plot. And it's also going to call that at the end of our animates function. Alright, so our animate function basically takes this linear space x. You can put the x outside the animate function. It should really not have any difference because it's not dependent on the index I, but our variable y, which is our function, is dependent on I, and our function y is just defined as sine of 2 pi times x minus 0.01 times the index value I, and then it's going to take this plot object line and it's going to set the new data of x and y to update those empty sets for new values of x and y. So it's going to update the linear space. Okay, it's going to take all those points in for the first argument, and then it's going to take the new values of y equals to sine 2 pi times x minus 0.01 times the index, and then we're going to instantiate the matplotlib.animation.func animation method, pass in as parameter the figure that we've instantiated up here, and we're going to also pass in the function, the animate function. Okay, and basically that's just the init function. We don't really have to do that. We can remove this and we can remove the init. It should still work. We're going to tell the func animation method that we want 100 frames and an interval of 20, and I can remove this blit true. Should still give us an animation. It's just going to take a while, and then I'm going to save the image as example 0 using the pillar write method by instantiating the save method. Alright, so here we have the graph. I'm also just going to suppress one of them by saying plot.close, so that I don't want to show two graphs simultaneously. And upon calling the animation object, it's just going to show one graph on our screen. Then if we play it, it's basically going to loop through this function here, which is a traveling sine wave. Okay, so that's really nice because what you'll see is something like this. Okay, that's cool because, you know, we had two different types of animations thus far. We had the animation where the sine wave was constructed progressively, and then we also have a traveling sine wave, which is a bit different. All that it's doing is it's moving the argument of sine by 0.01 times by the index I of each frame in the animation, and so we get this really cool traveling wave. So I'm just going to pause that. Once again, you can play around with some of the parameters on the axes, and you can set up your own titles and stuff like that. So here's an example of what I've done over there for illustrative purposes. I've just set the axis spines through 0 once again, and I've just chosen the axis labels to be at the top and the right. Again, let me also suppress that by saying plot.close and rerunning that all over again. Okay, so this time the axis has been set to pass through the origin, so we no longer have this box diagram around it. Okay, but we still have the same function. And if you keep looping through it, it's just going to do that. We can reflect. That goes back and forth forever and ever. Okay. And in the next piece of code, the only thing I've updated over here is the fact that I want my grid to appear as having the special angles and the corresponding output values for our special angles. So I'm just going to remove the return line again. And I'm also going to remove that init definition because that's really not necessary. That's a bit overkill and people do get confused by simple things like that. So I'm going to remove that. I'm going to remove this as well. Once that has completed rendering, you should see it over here, okay, in your directory. So here you go. Okay, it looks funny. It looks like it's rolling because the number of points that we specified is not that many. Okay, so in this next section, we're going to be looking at animations of 3D plots. So this is quite nice because we're now in a position to be animating three-dimensional graphs. And for this, we're going to use the same tools available to us in 2D animations and 3D plots. And so I'm just going to import all the appropriate libraries, which is going to be the MatPlotLib.animation, the NumPy library, the MatPlotLib.pyplot library, and I'm going to set the default animation rendering to animation.html to JS.html. And then I'm also going to import the MatPlotLib animation pillow writer libraries. Okay, and so by rendering that, really nothing's going to happen. I'm going to declare a mesh grid because we have here a linear space from -1 to 100 over 100 points, and my mesh grid is going to consist of these two dimensions. And then I'm going to declare a function z, which is x squared plus x times y. Okay, and so if I want to animate this, it depends what I really want to do, but what we're going to do is we're going to actually animate the view_init method on the axis, which was instantiated over here. So we're going to plot_surface, and we're going to set the initial view_init method to the elevation angle of 10 and azimuth angle of 10. But then we're going to update that using the animate function by passing that into the func animation method, passing in the figure object, passing in the animate function, and then specifying the number of frames to be 100. And then setting the interval equals to 50. Okay, and so then it's also, we're going to also save the animation by using the pillow write method. So here I've specified the file name animate3d.gif. I've also specified the writer as pillow, and that should be enough for us to be able to render the graph fast. And it's going to give us this beautiful three-dimensional graph. Okay, so here's the result. But upon playing that animation, it's going to rotate in 3 dimensions, and then you can see that the axis labels will jump to the other side once it gets to a certain orientation, so as to maintain clear visibility at any given orientation of the graph. So yeah, this is pretty cool. I hope that these tutorials were really helpful in helping you become a better presenter and you being able to produce better content. Yeah, this is all for this series. This is just a sort of the friendly introduction to the tools that we might require to be able to do more difficult simulations, actual real world problems, so that we don't get stuck with any of the tools that we don't have. So we need to really make sure that we really have all of this before we go into further detail. Okay, so yeah, that's it for this series, and I hope to see you in the next series.